Hello everyone, good to be here again. My name is Maksymilian Operlejn, and today we'll continue with the topic of training on noisy labels. So this time we will focus on more advanced methods. So before we start, as you saw in the title, this is part 2. So the first one is of course on our YouTube channel, already public, also on our website in the blog part. So well, I encourage you to watch it. So the first part, but also other deep talks. So I watched almost all of them, and they are very, very nice. A lot of good knowledge. So I definitely recommend watching all of them. Before we start, a little reminder of what was covered in the first part. So initially, I talked about how the noise actually reveals itself in the labels. So we got a picture of some young gentleman right here. It's actually a picture from the ImageNet database, and you can see it was annotated as nipple for some reason. So that's basically, so noise in labels is just when the label isn't real. So it is something else that then it is for real in the image. Right, so yeah, I talked a little about where the noise in labels comes from, the troubles it causes, as well as the types that we can encounter in our data. The image on the right I took from Survey, which collects all proven methods and divides them into some branches, as you can see. So previously in the part 1, I presented the loss design methods. So just by modifying a few lines of code, we could improve the results and make our network more robust to the noise in labels. So basically this time we will present all the other branches. So robust architecture, robust regularization, and sample selection. They are a bit more complex, but they are very, very effective. So moving on to the agenda, we will first start by presenting sample selection and robust regularization methods. Although they stand far apart from the current state of the art, they provide a foundation for better and more complex methods. So we need to talk about them for a little bit before these advanced methods. So then I will present you like 3 very important and very powerful architectures for dealing with noise in labels. Then I will obviously share my conclusions and also provide you with all the papers and all the links I used while creating this presentation. So of course, due to the time limitations, one more time, I will just present you a high-level overview of everything. So if you're interested in the topic, I can answer all the questions after the talk, or maybe you can write me an email or private message, or look at these references. They are very, very nice. All right, so let's move to the sample selection methods. So it's time to briefly introduce you the multi-network learning, which is basically the training or learning on multiple number of networks. So first of all, I would like to present you MentorNet, which was created by researchers from Google in 2018, if I'm not mistaken. So to know what MentorNet is, we need to learn a bit what curriculum learning is. So curriculum learning, especially for machine learning, is a training strategy that trains a model from easier to harder data. So let's maybe translate it to the example of human beings. So as we know, it's easier, and we should start from the basic mathematical operations first when we are learning mathematics. So maybe addition, division, etc. Then we can move to the algebra, and finally we can we can be taught, or we can learn calculus. So we need to learn easy things first in order to learn the more complex ones. So the same assumption is with the MentorNet. So basically we got two networks. One of them, MentorNet, is a network which will create a curriculum, so a strategy to learn. So MentorNet, the teacher, will give filtered samples to StudentNet, and the curriculum by which it operates will be created by approximation of existing curriculums, but also by discovering new ones from the data. So, for example, we can give a small clean data set to the mentornet, right? And it will learn a curriculum, so the strategy, and then we can introduce the new data set, so maybe the bigger and corrupted one. And the mentornet will already have a strategy to learn it. So the data, the corrupted data, is is going as an input for the student net. It will pass it to mentornet, and then mentornet will extract weights. So the higher the weight, the easier the sample is. So basically, we want to select and learn this easier sample first, and then move to the more difficult ones. So that's the way the mentornet works. And then for the testing part, so for the evaluation, only student.net will be used. So we are not using any curriculum this time. We are just using the student.net for the evaluation. Right, so it's mentornet. It's all cool, but the curriculum part is a little too complicated, and it requires much more work to do. And there is another method called co-teaching, which was actually published, just after the mentornet. And this time we also got two DNNs, but it is starting from the different assumptions. So this time both DNNs are equal, so they have the same architecture. The difference is that they have different initial parameters and different data as an input data. So basically, we got two DNNs, and they will select samples with small loss separately. So they have both like some batches of data. Then we are selecting in both of them the examples with small loss, because we are assuming in this case that if the if the data sample will have small loss, then it probably should be clean. So we are assessing, let's consider it as a clean sample. So when we have this, small loss samples, then we are passing them to each other. So the peer networks will exchange data and update parameters that way. So the reason for that is to prevent confirmation bias. So it occurs when the model is becoming more and more confident that it is going in the right direction, even if it's not, basically. So, we don't want the model to, find the evidence to prove its point, because it can be closed in the bubble, and we will not know if the model is, if the model knows the case or not. So we don't want it to be too sure. That's why we got like two peer networks, which will help each other to be better. So the algorithm is pretty simple. This part is the most important one. So basically, we are collecting the subset of data for the model F and for the model G. Both of them are some percentage of small loss instances. So we are taking some amount of small loss instances. And then to update the parameters, we are using, for the model F, we are using the data from the model G, so selected by model G, and vice versa. For the weights of G, we are using the data of the F model. So that's how co-teaching works, and it will be a method which will be then used for more complex models. Then we got like some other methods, for example, decouple. So usually we are thinking about how to update the parameters. So we are thinking about some new loss function which can improve the results, and we are not thinking about when to update parameters. So this time decoupling is trying to think when to do it. So basically, in this case, we are only updating the parameters when the two networks, the peer networks, will disagree in prediction. So they will have just two different labels for one sample. Then we can update the both networks. Well, we got many other methods based on training two networks. For example, co-teaching plus is just applying decoupling to co-teaching, but I will not cover all of them because the most important method for us is, as I said before, co-teaching. So this concept will be used before. So basically, one more time, we are selecting the small loss instances, small loss samples, and then the networks are exchanging that data to update the parameters. So that's the way it works. Right, let's jump to the robust regularization methods. So there are many methods, once again, that actually work and make a network robust. So I have highlighted 4 of them here. I will discuss the first 3 quickly, so we will be aware of their presence, but we will look at the last one in more detail because it's like the best of them. So, for example, the pre-training, it has been empirically proven that pre-training on another clean set and then, fine-tuning on the bigger but maybe a bit corrupted dataset, so the dataset with noisy labels, can improve robustness, so can help us with the problem of noisy labels. So that's one thing. We also have something called robust early learning, which divides the parameters, the neural network parameters, into critical and non-critical. So we know basically that only like some portion of our parameters in the neural network will actually work well for predicting our classes. And in this case, there are some non-critical, which will then be used for a network to overfit, so to memorize the noisy samples. So we know that there exist these non-critical parameters, and then we are penalize them by some equation. So basically, we don't want them to be updated in a big proportion. So we are just updating the primarily, we are updating the critical parameters for our network. Then we got label smoothing. So label smoothing, for those who don't know, is, well, we have one hot encoded label, right? So for the normal classification problem, we got one hot encoded label, which, for example, says that the class third is, well, the true class here. So we are introducing some noise to the labels. So actually, we are adding some probability for all the classes, and this one is a bit decreased. So that's basically the label smoothing, and it prevents the model from overconfidence. So we want to address the problem of overconfidence, and this time the label smoothing is also very good for robustness. What is interesting is that this publication was from the Polish author, so it is very interesting. I encourage you to take a look. Also, at the end, as I said, the great method that is not yet widely known, but it is very useful for regularization, both on noisy and clean data. So we will look at the mix-up now. All right, so mix-up is data augmentation method with great regularization power. So this paper actually was released in 2017, but only now it is getting recognized because that the topic of training on noisy labels is rising in popularity. So that's why we are often using mix-up now. So the number of citations is rising dynamically, and the whole idea behind that is that training is done on pairs of mixed up samples and their labels. So this is the way we are mixing the samples. As you can see here, we got 2 images of a cat and of a dog. And then after applying mix-up, they will be, well, mixed, right? So as we can see here, the 2 images are overlapping. So that's the way we are doing the mix-up. As you can see here, the cat is more visible than the dog because we are randomly selecting the proportions of both images. So right here, as you can see, we got, let's say, 70% of the cat and 30% of the dog. So these are the labels. So previously, they were one hot encoded, and as in this case, we got them mixed, so in some proportion. These are the equations. As you can see here, we got the parameter lambda right here. So it's basically all about proportion of 2 samples and 2 labels. This is the code which was in the official paper, and it's very easy. So as you can see here, we are just drawing lambda from the beta distribution. So we are randomly picking the lambda for each for the data. Alpha is actually a hyperparameter here. So we got an x, which is mixing the x1 and x2 in some proportion, and the same thing with label. So in the image, we can observe that we have two classes, green and orange, and then we have like a decision area, right, in the blue. So the blue, the blue decision area is when the model will consider the data sample as orange in the orange class. So as you can see, the boundaries are quite strict. So for example, if we'll have a point right here, it will be considered as orange, but if we'll move a pointer a bit above, then it will be considered as green. So it's not a perfect situation. So in case of a mix-up, we got, a different case. So as you can see, the decision area is much more fuzzy, and we got a probability right here instead of just 0 and 1. So basically, that's what we care about. So the model is not so certain anymore of the assignment. So mix-up regularizes the neural network to favor simple linear behavior in between training example. Actually, you can see here on the results that we got like different architectures, and all of them are. So that the error rate for all of them is decreased using mix-up with the alpha parameter equals 0.2 or 0.4, depends on the experiment. So basically, there's a very good regularization method, not only for the noisy data sets, because right here, as you can see, these are the results for the clean data. And now we can move to the noisy part. So it turns out that mix-up also is robust to noise in labels. So because of the model's ability to prevent memorization, the authors claim that it should be easier to learn interpolations between real examples compared to memorizing interpolations involving random labels. So the results confirm that. As you can see here, the model achieves the lowest error rate for the mix-up versions. What is also interesting, it's not like we need to use mix-up or dropout. So mix-up instead of dropout, we can use both of them, and it usually decreases the error or increases the result even more. So that's a good thing. So it's a very simple idea. It's good to know that in the era of a huge neural network, we can still discover some simple idea which are very great and working very well for our case. And one of the people on the first part of the deep talk asked me if I used any of these methods, so the methods of training on noisy labels in practice in a commercial project. So I need to tell you that it just happened to me recently. So although in the project I'm dealing with tabular data and mix-up was mainly created for the image data, I just wanted to try it, and the results, so my model improved in accuracy for my problem. So I can definitely recommend it as a very easy but very powerful idea. Right, so now we can move to the advanced techniques. So as I said, we will now describe 3 architectures. All of them are very similar, so we will see in a minute. First of all, we got divide mix. So divide mix is actually an architecture developed in 2020, and it consists of several elements that we learned earlier. So we got co-teaching and we got mix-up. But there are some elements, some components that we don't know yet. So there's a Gaussian mixture model and mix match. So I will just try to quickly tell you what is going on with these two. So what is mix match? Mix match is a semi-supervised classification method. So it was originally created, so the purpose of such training was to use large data sets that are not labeled. So we can imagine that nowadays we got a tremendous amount of unlabeled data. So why not to make use of it, right? So basically, we have two inputs for the whole model. So we got, let's say, small labeled data sets. So for example, Cypher 100 or something like that. And then we got potentially much bigger but unlabeled data. And we want to utilize that, right? So for labeled data, the training is done in a standard way. So we got a cross-entropy loss, and we are just dealing with just a normal classification problem. And the interesting part is with the unlabeled data. So we are applying something called labeled guessing. So label guessing. So what is label guessing exactly? We can see here on the image the whole process of label guessing. So as you can see here, we got an unlabeled image. So we don't have a label, we got some image, and then we are applying K augmentations to it. So it's just a regular stochastic data augmentation. So rotating, flipping, cropping, etc. Right? So using the supervised part of our model, so trained on these labeled examples, we are classifying our augmented images. So we got some predictions, then we are averaging it, and we are sharpening the results. So by sharpening the results, I mean, we want to minimize the entropy. So we want one prediction, so one class to dominate with of another, right? So we want one of them to be confident, and that's the way the sharpening works right here. So then what we will do is to compare this result, so the averaged and sharpened result for all these augmentations, with the original unlabeled image. So we are doing it, so we are introducing the new loss function, which will be in this case squared error, and that's because we want to have it restored. So even if the augmentation was applied, we want to the model to have the ability to restore the augmented image to the original one. So that's the part of the unsupervised, let's say, learning. And we are combining both losses. So we got cross entropy from the supervised way, and we got this squared error for the unsupervised. We are combining both of them, and this is the way it learns. So we got mix-up at the end, which is applied, and well, it serves as a data augmentation and also the regularization method. Right, so as you can see here, one more example why the mix-up is very important for all these architectures. You can see some ablation tests right here, and they tested how the mix match would perform without mix-up. So we got the error rate of 39.11, and actually applying mix-up to labeled, unlabeled, or both data, it's reducing the error to 12.26 from 39. So it's a very big decrease. That's why the mix-up is a good method for us. So that's all cool, but how does it really relate to the training with noisy labels? So you may remember this graph from the previous section, the previous part of the talk. It shows the distribution of loss over the network training, right? So here we got the loss distribution for the clean data, and here for the noisy one. So we know that the model will start by by having smaller loss and converging quicker for the clean data, and it will be robust for a little bit for the noisy, but at the end it will overfit. So the part that we are interested in is right here. So as you can see here, the loss is clearly distinguishable for the noisy and clean data, right? So for example, here, taking this epoch, we can say that we can say with a good probability that the sample is clean or noisy. So then the labels can be removed from noisy samples, from these ones, and we can leave the labels for the clean dataset. And with that, we got two datasets, unlabeled noisy and labeled clean. And then we can perform mix match, to just do a simple classification. So the question now is how exactly we can separate the data into noisy and clean right here. So the answer is a Gaussian mixture model. So it's basically a clustering algorithm, but instead of closed clusters. So for k-means, we are just comparing the distances, to the clusters of all data points, and then we are assigning them, and they are in the cluster or no. In this case, everything is based on the distributions. So, we are assuming that points are generated from a mixture of distributions. So right here you can see that we got like different distributions, and the points are generated using them. So the algorithm is rather simple. So we are randomly initializing the clusters by mean and standard deviation, and then we are assigning the points. So we can see that this will be yellow for sure, and this will be a bit yellow but rather blue, and this will be still rather blue. And then having the points clustered, then we are calculating the mean and standard deviation once again for our clusters, and we'll go on and on until the clusters will be optimal at the end. So we are basically fitting the distribution curve for our data samples. So this will be used for dividing our data set into noisy and clean. So as you can see, we can take the epoch X right here, and we can plot the distribution. So let's just imagine this is the distribution for the epoch X. And then we are fitting the Gaussian mixture model, and we will have a probability for the data sample of being clean or noisy, right? So with this model, we can just input the data sample, and the model will tell us. So, for example, there's a 90% probability that it is actually clean. So with that information, we can divide the data set into clean and noisy, and then we can, easily work with that. All right. So now finally we can move to the description of divide mix. So as I said, it's like all these components are used to this model. So first of all, we got two models to prevent confirmation bias as with co-teaching. Then we are using Gaussian mixture model to divide the data into the clean labeled one and this noisy unlabeled one. And as you can see, we are exchanging the data between the two models. Then the training is done with a mix match, obviously. So this time we have the unlabeled and labeled data. We are doing mix match. So in a semi-supervised manner, we are achieving the convergence, right? And at the end, mix-up is here for the regularization purposes. So that's basically divide mix. So we are just, joining some components, and everything works very, very well. So it was actually a state of the art for I think 2 years, and it's still very popular to use this method because it's very popular. Then we can ask a question. So, okay, we got a noisy sample, but is it really noisy? Maybe it's just hard to classify it. Maybe the label is hard, but it is still the clean one, right? So we can see the distribution right here, and we can see that the distribution for the clean data and for the noisy data is overlapping. So right here is the region where we are not sure if it will be clean or noisy. So that's the thing that the prior guided denoising framework will address. So it's once again is very similar to divide mix. So once again we got a Gaussian mixture model used to divide into datasets. Well, it's not so easy. It's not just Gaussian mixture model, but we don't have time to explain it in detail. So you can look for the paper. So the most important thing is it's very similar. So we got two networks as in co-teaching. We got mix match used for semi-supervised learning. And the key difference is the division into easy, hard, and noisy datasets instead of just clean and noisy. So as you can see, we got the addition of the hard dataset. So we can look at this image once again. We got two distributions, clean and noisy. And then, we can, this is just for one epoch, right? But we can plot it throughout the whole training period. So basically, throughout the whole training, we will have some, different probability of the data being clean. So that's the way, that's the thing that we care for. So we got these plots, as I will just I'll explain in a bit how it looks, because we got the the whole training for this one sample, we are having the probability of it being clean, and we can assess, for example, for these ones, the probability of the sample being clean is very high throughout the whole training. So we are assuming that it is clean, so easy data set. Here we got the probability of it being clean very low, so from the beginning till the end of the training. So we are assuming it will be the noisy data set. And this one is when the probability is changing over time. So first of all, it's high, and then it will be lower and higher, etc. So as you can see here, they are classified as the hard ones. So once again, because we are still using mixed match, so for the easy ones, we are using the classic cross entropy for the easy ones, the squared error for the noisy ones, so the same as in mixed match. And this time we are combining both of these, so the cross entropy and squared error for the hard sample. So we are just combining two losses for that one, and then we are combining all three of them to provide us with just one loss. And now finally, the last method for today is PROMIX. It is based on, once again, very similar principles as divide, mix, and PDGF, and it has three advantages. So first of all, we still got the semi-supervised training. This time we are using fixed match instead of mixed match. So it was proven that sometimes we can have a problem with mixed match in case of regularizing the hyperparameters, and fixed match will solve this for us, and well, it will have better results for the semi-supervised learning. So you can learn about it in this paper. Very interesting thing for me, at least. So the PROMIX, so that's the first advantage. Another advantages is, for example, the small loss selection. In this case, we are using class-wise small selection. So we are having the whole training set, we're having the network, and then we are selecting the small loss to the clean data and the high loss to the noisy data. This time we are using it in a balanced way. So we want all classes to be distributed equally. So we want to have a representation for all the classes. So that's the first thing. The second thing, and then as you can see here, we got a clean set. So this goes straight to the clean set. And for this instances with high loss, we can predict it using this supervised parts as before. And then when we have this prediction, we can see if there is a high confidence towards that particular example. So for example, we have a prediction right here, and we got some threshold which will assess if the prediction is very sure, so with a high confidence or not. So if it will be above the threshold, then we can assume that this particular sample can be considered as this class. So we are basically moving it from the unlabeled dataset to labeled dataset forever, because we know that we have a high confidence towards that. And one more thing is that once again we got two networks, and they need to agree on that high confidence selection. So not only high confidence, but also the agreement between two networks. So both of them need to be sure that this particular sample should go into the clean set. And once again we got the same methods, so semi-supervised learning on this data set, and everything looks smooth. So at this point, PROMIX achieves the best results, but it's worth considering that we got different benchmarks and different types of noise. So it probably will not always be the best, because it was tested on Cypher 10 and Cypher 100. So here are some recommendations from me how to assess the problem of training on noisy labels. So I would start small. So even by modifying the loss function, as you remember, I was describing it in the first part. So it's a very simple method. We are just changing a few lines of code, and it can already help significantly. So for example, I would use active passive loss or something else from the first presentation. Then we could apply the data augmentation using Mixup. So it's once again, it's like another block of code which will help us to prevent noisy labels from being memorized, and this should help even on clean data. So not to mention data with moderately noisy labels. So I'm adding this moderately part here, and it's basically because it's not always great with Mixup to work on heavy noise. So for example, when we have 80% of noise, Mixup will not work well. Right, so the methods with semi-supervised learning are outstanding. So I would end in this point to just try some semi-supervised learning for our case. I would start with divide mix. As I said, this paper is widely known and it's rather easy to read and comprehend, and also implement because we got the GitHub repo with the whole implementation. Then, to improve the results even more, you could test PDGF or PROMIX, so the last two methods. And as I said, the PROMIX was only tested on Cypher 10 and Cypher 100, and actually the PDGF was tested on more complex and bigger data sets. So, and it achieved very, very good results. So I would test, one of them, right? And then for labels with very high noise, there are some modifications to divide mix. They are being developed right now. So we got a sample research paper right here. It's dated February 2023, so 1 month ago. And by applying some nice tricks to divide mix, so the regular divide mix, we can achieve very good result on the heavy noise. So for example, 80 or 90% of noisy labels. All right, so here are the benchmark results for some sample data set. As you can see here, we described the forward T in the first part of the presentation, and we described the co-teaching, divide mix, PDGF, and PROMIX in this part. So we covered all of them. You can take a look if you want for the implementations. Summary. I realized that the methods have been discussed very briefly and without details. So of course there are much more methods, and this survey will serve you well if you want to get to know with the training on noisy labels. We got 62 robust training methods, and approaches are evaluated by 6 different criteria. So if they are well on heavy noise, on complex noise, etc. We got some noisy data sets, evaluation metrics, and also the promising research directions for the future. So there are plenty of ways to deal with noisy labels, and the attempts are taken to approach the problem from different angles. So we described the loss design in the first part and 3 of them in the second part. The best methods use a mixture of the basic ones. So as I said, the combination of semi-supervised learning with some regularization methods and also sample selection methods are very great and achieve SOTA results. So the choice of the best method is based on an examination of strength and type of noise. So as I said, it depends if the noise is very, very big, so the proportion of the noisy labels is big or small. I gave you my recommendations on that. And for me at least, it's an interesting research path with much left to explore. These are the references, all the papers, all the links. Everything is provided right here. So that's it. Thank you very much for your attention.